This video will cover random forests. By the end of this video, you should know what a random forest is, how random forests differ from regression trees, what some advantages and disadvantages of random forests as a modeling tool are, and how individual training data samples are constructed for each tree in a random forest. You should remember regression trees from a previous video. These are a simple example of a classification of a regression tree or a CART algorithm. A regression tree is a tree-like flowchart ending in leaves. Each branch splits the data based on the value of a single feature. Forecasts from these trees are the in-sample average of all observations in a given leaf. You should also remember that we don't generally use regression trees in practice. In principle, they can lead to very flexible models. But in practice, regression trees don't perform very well for forecasts. What happens is you sometimes will create a leaf based on very few odd observations in your data, and that leads to poor out-of-sample predictions. But if regression trees sometimes produce odd predictions, what could we do to address that? If you have a model that occasionally produces odd forecasts, you could cross-check its forecasts against another version of the model. If the forecasts for the two models are similar, you might feel comfortable with the forecast, but if the forecasts are different, you might start to worry. But if you know to worry based on the forecast from these two models, what should your forecast be? So suppose that you have two versions of a model that disagree substantially on a forecast. If you had a third model that you could compare it to, you could look at each of those forecasts and use the one that's the closest to the forecast from the third version. This is one example of an ensemble method. These are methods in data science and machine learning for combining many versions of a model to improve forecasts. In this example that I've just given you, different models are voting on a forecast, and you're taking a forecast closest to the one that the most models vote for. Suppose, though, that you don't just have three models, but many, maybe hundreds of models or thousands. What's a reasonable way to aggregate the forecasts from all of these models into a single forecast? One approach would just be to take the average of all the forecasts. If weird predictions from individual models are uncommon, they should average out against the not weird predictions from all the other models. This is precisely the ensemble method used by random forests. Random forests are an ensemble of regression trees, generally hundreds or thousands of different regression trees. Each tree can compute a forecast for a given set of features, following that regression tree flowchart. The forecast from the random forest is the average across all of the trees. A random forest consists of many different regression trees. These are each different models. But where do they come from? How can you use one dataset to construct hundreds or thousands of models? Dividing your data into hundreds of tiny datasets doesn't make efficient use of the data you have. It would probably lead to low-quality forecasts. Random forests solve this problem by creating data from many models using an ensemble method called bootstrap aggregation. Here's how it works. Suppose you have a large dataset with n observations and k features. You're going to use the following procedure. You randomly sample n observations from your original dataset with replacement, so individual observations might be repeated in your data. You're also going to randomly select a subset of your k features. This new dataset has n resampled observations and a smaller, less than k subset of the features. You're going to use this new dataset as the training data and then grow one regression tree. You then repeat this process of randomly resampling your data, randomly selecting a subset of your features, and then training a regression tree hundreds or thousands of times. It's this combination of regression trees and bootstrap aggregation that form the basis of random forests. They're a collection of regression trees, hence the word forest, and the subsample of features and observations used to grow each tree are randomly constructed using bootstrap aggregation, hence the random. Random forests as a modeling tool were first characterized in the 1990s. They've been in widespread use in predictive modeling ever since then. And that's because they have some rather strong advantages as a modeling tool. They place weak assumptions over the relationships between the features and the labels. Unlike OLS or Lasso, which assume a linear relationship, there's no such assumption underlying random forests. They have very strong out-of-sample performance. They generate really good out-of-sample forecasts with comparatively little input by the data scientist. Random forests are also robust to training data with many features, so you worry less about the feature selection problem with random forests. In general, random forests require fewer decisions on the part of a data scientist than some alternative models. And finally, random forests are computationally simple to implement when you're using MSE as your loss function. This is because the process of deciding on which feature and what value define each split in each regression tree can be converted into a relatively simple formula when you're using MSE as your loss function. So why don't we always use random forests? There are also some disadvantages to random forests as a modeling tool. Importantly, a large number of trees is required for strong forecast performance. This leads to large computing requirements. And it also means that giving your models to somebody else or exporting them can be very difficult because you have to give them a copy of every regression tree you construct. Those might number in the hundreds, thousands, or maybe many more. Random forest models are also a black box. And what I mean by this is it's very difficult to take the model apart and say why you obtain a particular prediction. That's because you're averaging across many, many regression trees. So thinking about how changing a particular feature might change a predicted label is really not straightforward when using random forests. Random forests also don't deal well with categorical data. So if you have data that don't fit neatly onto a real number line, it can be difficult for random forest models to generate forecasts with those data. Many modern random forest algorithms that improve upon the original algorithm also have many hyperparameters. This requires tuning already computationally complex models and can be very demanding on your computer systems. The original random forest is just a combination of regression trees and bootstrap aggregation. There are many extensions to random forests that are used in the modern machine learning and data science world. Most random forest algorithms now add regularization methods, such as pruning. You may see other ensemble methods with random forests, such as gradient boosting. They may implement alternative loss functions. There are alternative methods of determining the optimal split, such as honest trees. And there are also alternative methods of computing the forecast in each leaf, such as generalized random forests or moment forests. There's active research in the science of machine learning on all of these methods. Statisticians and machine learning experts are working to characterize properties of these modeling tools, such as, do they work? Or, will they tend to choose the correct model if they're given sufficient data? This is a really important property for any sort of modeling tool. You'd like to know that as you add more data, you're much more likely to get closer and closer to the correct model. There's also analysis into what are the properties of the forecast from these models. For example, are the forecasts accurate and/or precise? And do the forecasts get better as you add more data? For many of the random forest modeling tools out there, these questions have not yet been answered. However, in the late 2010s, statisticians were able to demonstrate that under correct conditions, random forests will choose the correct model. Also, forecasts from these models get more accurate and more precise as you add more training data. These results come with some assumptions. In particular, it requires that you use random forests with bootstrap aggregation and honest trees. Honest trees are a leaf-splitting algorithm that only recently has come into use in random forests. And in fact, the random forest algorithm that we'll consider in this class does not use honest trees. So as you can see, these methods are still areas of active research.